Hi everyone. Today I'm gonna talk something about BERT model serving on NVIDIA's GPU. So from 2018, BERT and its variants become widely adopted and served online in China and among the world's top companies on NVIDIA's GPU. In a online system, we usually would like to fully utilize the GPU and meet the target latency, which means the quality of the service. However, the original BERT implementation is not very efficient on GPU and not using latest software and hardware features of the GPU, such as Tensor Core. So for NVIDIA, we developed optimized code for the inference using TensorRT and handwritten CUDA. Additionally, with today's key role, Triton Inference Server, you can deploy the inference efficiently on GPU. Triton was previously named the TensorRT Inference Server, but just in last week, we renamed it to Triton Inference Server. For your reference, in this talk, you might learn the key features of Triton Inference Server and how it serves the optimized BERT code. My name is Tianhao from NVIDIA's Solution Architect team. So today's agenda will be split into three parts. The first one, we will go through the features of the Triton Inference Server and try to deep dive into some of them. And then we will go through the case study to discuss the FasterTransformer 2.0 version and TensorRT. They are both the implementation of the BERT optimization. And we will discuss about how to deploy these models efficiently with Triton Inference Server. And the third part is about some discussion on very cutting-edge state-of-the-art models. And if we have time, we will have a Q&A session. So for a GPU hyperscale inference platform, it's typically composed of three parts. The first one is the hardware. Here we will use Tesla T4, and it's the world's most advanced scaled GPU. And then we will have the software. NVIDIA developed TensorRT as an inference framework to help you accelerate your model inference. And at last, we will have Triton Inference Server. That's very important in your deployment to serve your models online. So about Tesla T4. It has the new Turing Tensor Core, and the new Turing Tensor Core will handle a 4x4 matrix tile multiplication efficient within one instruction at 130 teraops in int8 precision, and it even has int4 capability. NVIDIA also released several how to run inference of less than 50 in int4. And with just about 1% accuracy loss. So compared with previous Tensor Core introduced in Volta architecture, Turing Tensor the additional ability of run the inference in. So about TensorRT, here's a list of the of its key features, such as a quantized int8. It significantly improves inference performance of models trained in FP32 for precision by quantizing them to int8 while minimizing the accuracy loss. And it's very important features about the layer fusion. It tries to optimize the graph, its utilization, and optimize memory storage and the bandwidth as well. By combining successive nodes into a single node and for the single kernel execution. In our later case study, we will try to discuss on it. And TensorRT will also try to select the best kernels for each layer for the target platform, such as Jetson, Tesla, or DrivePX GPU platform. And with dynamic tensor memory, it reduces memory footprint and improves the memory reuse by allocating memory for each tensor only for the during its usage. So TensorRT will also reduce the memory footprints, and you can deploy more models on single GPU or deploy larger models on the GPU. And another feature is very important. It's multi-stream execution. This feature is related to the concurrent model execution feature that will be introduced later. It's also a key feature of Triton Inference Server. Let's have a look at the basic inference server architecture. Triton Inference Server adopts a client-server structure. User sends requests from client to server via HTTP or GRP endpoints. The server will manage the model repositories, the GPU resources, schedule, and execute inference. A lot of framework backends are supported, such as TensorFlow and TensorFlow TensorRT, and TensorRT, Caffe, Onyx, PyTorch, and we also support running these frameworks on CPU if the framework itself supports it. And Triton will also manage all the GPU resources in a single node and balance the workloads, and this is very important for your deployment in the data center. We have a lot of features focusing on utilization, usability, performance, and customization. I'm going to share details of some features. The very important thing we want to know is that how about the usability and why it can serve your models efficiently on GPU. We have very key part. So before we going deep into these features, here's one question: what is utilization? Here it refers to the percentage of a time period where there's active kernels on GPU. A kernel is something like a CPU function. Here are some timelines. It's very ideal and simplified, and it's used just as an illustrative example here. In this timeline, block in yellow means that the GPU is idle. Usually it's waiting for some CPU tasks or waiting for kernels to be launched from CPU to GPU. Block in green means kernel is active on GPU, and the length refers to the time span. So in real case, you can use NVProf, NVVP, N-site systems. These are tools provided by NVIDIA, file the application and get a similar timeline. And N-site systems will be used in the case study later. So in the baseline, the idle time equals to the busy time. This is an assumption here. The utilization sampled here is 50%. Of course, not fully utilizing GPU. So the question is how to improve it. The most basic one is batching. If you have a batch size of 5, your task scale becomes 5 times. For a GPU, it has thousands of cores, and typically a larger task execution might have higher efficiency. So execution time won't be 5 times and could even only increase a little bit. Here we assume executing kernel with batch size equals 2 only increase 50% of the execution time. It comes like this in the second line. It reaches 60% of the utilization, and it can also save total execution time because the kernel is of higher efficiency. But here, for in simplicity, we only discuss the utilization. The second one is concurrent model execution. With concurrency, the overlapped execution helps hide the kernel launch time and idle period. On GPU, we have 2 methods, the multi-stream and MPS. For GPU, just something like multi-thread on CPU, GPU use streams to schedule GPU kernels. So different kernels in different streams might run concurrently on GPU. So the multi-stream might allow you to run kernels concurrently within a single CPU process. But if you cannot support multi-stream, the option to run kernels concurrently on GPU, it's called MPS, multi-process service. Multi-process share the same CUDA context. Actually, for a CPU process, it holds one CUDA context. So if you have multiple processes, you usually have multiple CUDA contexts. But on a same GPU, there's only one active CUDA context at a time. So if there are multiple CUDA contexts, you have to switch between these contexts. So actually, the kernels on the GPU are not executed concurrently. So MPS will let you share the same CUDA context so that you can make it as an agency to run kernels concurrently on GPU. But risk is that if one process is done, and all the processes might run into error. And in this case, with two instances, the concurrent model execution can give you a utilization of 69%. And then we will have a question that, can I reduce the idle time, which means the yellow block here? Actually, CUDA graph is something like this. It's introduced in CUDA 10, and it will try to launch kernels directly with a graph launch. So that might reduce the kernel launch time, and here the yellow block the span of the yellow block might reduce. So with CUDA graph, the utilization can get to 67%. And as we previously discussed on the TensorRT, it has the ability to fuse kernels. I assume that the kernel A and kernel B can be fused together. So after the fusion, there might be only two kernels. And even if the kernel launch time and the idle time are not reduced, the whole timeline's utilization might reach 56%. By combining the CUDA graph and the TensorRT feature together, the combined utilization can be 71%. So in scope of the utilization, you have several methods to optimize, and these methods are related to the features in Triton Inference Server. So let us go deep into the features provided by Triton Inference Server. The first one is dynamic batching scheduler. Actually, this is it's part of the batching method. For most online systems, the incoming requests are not of the large batch size. It usually has a very small batch size, and the different requests might be different from each other. So here we have a dynamic batching scheduler help you to group different requests into a single request. So that in this case, we group 4 requests into 2 requests of batch size 4. Then the execution might be more efficient than the previous batch size 1. With dynamic batching, here's a performance comparison. If you has no dynamic batching and the incoming batch size is 1, then the yellow figure relates to this situation. The ResNet 50 inference can have about 500 throughput. And if the incoming request is of batch size 8, means that the static batch size 8, and we also don't have dynamic batching, and the red figure relates to this situation, and the throughput might be over 1,500. And the blue one relates to the dynamic batching scheme. You see, when the incoming requests are coming at about 16 concurrency, the performance or the throughput of the inference might be similar to the static batching. So the second one, the concurrent model execution support in Triton Inference Server. As we just talked about, the concurrent model execution will help you reduce the idle time on GPU, and you can also handle multiple ways of incoming requests at the same time. And in Triton Inference Server, usually we will have multiple execution contexts, and we will assign a single thread for the single execution context. And usually we will arrange one CUDA stream for that. So the scheduling, so we have multiple threads to do the scheduling, and we have multiple streams to run the task on the GPU simultaneously. With this configuration, we have another option is a model priority. We can set different thread priority for the scheduling threads, and we can set different stream priority for the multiple stream. So with this configuration, you can give a certain model a higher priority over other models. Then this you can test this with some cases. We also have a model control and model configuration method. Currently, we use file system to manage the model repository, and we give some options to control loading and unloading the models in some specific way, such as the load all models at runtime, or you have to explicitly load the models you want. This is allowed with the option provided in this slide. Additional to the previous configuration, we have to write a config.pbtxt file for each model, and this configuration file will control the how the model is deployed with Triton Inference Server precisely. So in the left half, these things are very basic, such as the model name and the model platform. Here we use a TensorRT plan file, and you have to set the batch size. And we also try to define the input and output. The version policy here control which model version should be loaded. This is very helpful when to load or unload some models in flight. And on the left half, we have very important configurations. The first one is the instance group. This one will control on which GPU you should deploy this model to, and the kind will define the executions on CPU or on GPU. The count is referring to the concurrency, which means we will launch multiple contexts for this model. And the dynamic batching is very simple but important. The max Q delay microseconds will help you control the max Q time so that you can still meet your SLA. The optimization section is very interesting because here are a lot of optimization methods put in this section, such as the XLA of TensorFlow and the TensorFlow TensorRT, and also the CUDA graphs I mentioned in previous slides to optimize the TensorRT inference with CUDA over 10. And the priority is also set here to control the model priority. Actually, you can refer to the documentation for more options about the optimization. We just mentioned all the CPU workloads are supported if the framework itself supports it. So you can also deploy your CPU models with Triton Inference Server, and that might benefit from Triton features such as multiple model framework support and dynamic batching, custom backend model ensembling, and also the audio streaming API. We provide a lot of available metrics for you to query. It's of different granularity and different frequency. And with these metrics, you can easily monitor your server and monitor the deployment. Another important thing is the perf client tool. This tool can help to generate faked data and use these data to profile the deployment. And this is also used in our later slides to have a case study. The results profiled by the perf client or the collected by the perf client tool can be exported to a CSV format file, and you can import the CSV into some other post-processing softwares to analyze the detailed composition of the inference time. Apart from these features about utilization and usability, we also pay a lot of attention to performance and customization to allow you to extend this Triton Inference Server. We have library version for you to easily integrate it directly into your application, and we also have custom backend to help you extend the Triton's ability, such as you can write a custom backend for the pre-processing or post-processing of the image. And you can also use a model ensemble to define a pipeline of the model executions so that you can, within a pipeline, you don't have to control more about the different steps of the pipeline. The Stream API might be very helpful when you serve some audio models. It's a built-in support for the audio streaming input, and usually it's in a speech recognition or a speech synthesis application. So based on the very basic features and important features of Triton Inference Server, and we've also discussed about how to improve the utilization and improve the GPU efficiency of the deployment. And next, we might go into the second section, and we will talk about the NVIDIA's BERT solution and how to deploy them with Triton Inference Server. So what's in BERT? I think everyone here might be very clear about what's inside BERT. It's a transformer encode, and it's become quite popular and widely adopted since 2018. So in BERT, in BERT 4, the BERT base, there might be 12 transformer encoders, and in each encoder, there are multi-head attention and V4 network. And within the multi-head attention, there might be some matrix multiplication, and the composition is very easy. And today we will not pay much attention to what's in BERT and what's BERT, but we will talk about the NVIDIA's optimization of BERT inference. So we have challenges, and we also have ideas to face the challenges. Currently, there are problems with BERT TensorFlow inference. You know, TensorFlow OPs are very small, such as GLU and layer norm, and the kernel launch causes much time. In a later slide, you might see a timeline of that. And the multi-head self-attention lacks efficient GPU implementation. The third one is that BERT code doesn't support FP16 inference natively. Just as we previously mentioned that on Tesla T4, we have the new Turing Tensor Core. We can run FP16 multiplication on Tensor Core with 8 times to peak performance to compared to FP32, and we can even support inter 8 Tensor Core multiplication. So we have to implement some code for the BERT FP16 inference. So the optimization ideas are very clear. The first one is to optimize the calculations with handwritten CUDA. Integrate the implementation to TensorFlow with the custom OP. The second one is to optimize the inference with TensorRT, because you know TensorRT has a lot of features to help you optimize your model, and of course it includes BERT. And for some kernels that are not very efficient, we can also write plugins for TensorRT, and that's how we do in this case. Apart from these two optimization ideas, we also have some algorithm level acceleration that might be contained in the open discussion. For NVIDIA, we generally have two implementations. The first one is the FasterTransformer, and it's open sourced under Deep Learning Examples repo from NVIDIA's official registry. The FasterTransformer project adopts the handwritten code. It tries to accelerate the transformer encoder, and actually decoder is also accelerated in the latest release. Actually, but for today, we will only discuss on the encoder. And we also released a BERT TensorRT code. It's previously released under TensorRT open source project, and it's in its demo, and you can find the code in its 6.0 release. And all the case study today is based on this branch. The latest code has been moved to deep learning examples as well under the language modeling, the BERT code. These two things are very similar. They try to optimize the compute-intensive OPs in the BERT inference, but works and based on different Here we will go through the case study, and you can easily reproduce my results with the steps provided on my personal GitHub, because it's a lot of stuff to try to export models, try to prepare the environment. So I just put that in my personal GitHub repo. You can refer to that. I think there might be slides after this webinar, and we will go through the 4 steps easily and quickly here. So first, we will try to build the source code and generate the TensorFlow custom OP library. This is an important thing because we might use that to work with Triton Inference Server. And second one is trying to export the frozen saved model PB from the score task inference code. And what we need to pay attention to is that this implementation allows you to select gem kernels. So you have to prepare the gemconfig.in file to select the best kernels for the Tesla T4, and then arrange the exported model in a tree structure. In Triton Inference Server, we use file system to manage the model repository. About TensorRT, I think it's very similar, and because we have very detailed steps for you to generate the plugin shared library, and you have to prepare them for the Triton Inference Server's deployment, and follow the README to export the engine plan. Remember to export and serve it on the same environment and the same GPU card. Then arrange the model directory in a tree structure. And that's very easy. And I also provide the detailed reproduction steps on my GitHub. In Triton Inference Server, you have to organize the model files in a structured tree, like the left part, and we have also to provide the configure pbtxt files for the FasterTransformer's deployment and the TensorRT's deployment. And you can get back to this slide after the webinar to see what's actually in these 2 config files. Then we have to launch the Triton Inference Server. We will try to use the Docker images from NGC. NGC is NVIDIA's GPU cloud. It's a registry, and we've already provided the TensorRT server for you to reproduce the results. And remember to use the same environment so that you can easily get the same result. And you know that for Triton Inference Server, if you have some external library, you can use LD preload environment to preload these shared libraries so that it can work with the Triton Inference server. Launch the server is very simple, just with the second command, as a third command. These steps are also included in my GitHub, so don't worry about the reproduction. Then I mentioned that we have a perf client tool. This client tool will help you generate the fake data. It can also send the requests in parallel to the server and get profiling results. The profiling results looks like this, and it reports the average latency, and it can also report the composition of the average request latency, such as the overhead, the queue overhead, and the compute overhead. So let's go into the detailed case study. First, we will use FasterTransformer, and we use scored task. It's stand for question answering dataset, and the optimized target is to max QPS, which is a throughput in an offline situation, and the batch size is set to 1. The hardware Tesla T4 and Intel Xeon CPU E5 2670. This is a hardware configuration. So first, we will try to run the inference on CPU. On CPU, it's not very ideal, and you can see that the QPS is around 10, and the average latency might be over 100 milliseconds. And the concurrent here means that we will launch several here's 4 threads to run the inference. And you can see that the basic result. Next, we will use try to run the inference on GPU with the original BERT code to see what is the problem with the inference. The precision is also FP32, and you can see that the QPS is raised to about 52.5, and with only 1 instance. The timeline here is generated by on-site systems. Let's look at the inference over time. Based on the previous discussion on the timeline, you can see that there's a lot of idle time, actually. And I also give a detail of encoder layer 3's execution. There you can see the idle time is even longer than some of the kernel execution. So based on this, we have a lot of things to do to optimize the inference. The first one is using FasterTransformer. FasterTransformer try to write the compute-intensive OPs to get it to running on GPU efficiently. So the QPS can be raised from 50 to around 100, and the latency is dropped to around 10 milliseconds. It looks very much better, and we can look at the inference over time. There's still idle time between different inferences because you have to prepare for the next inference and copy data from host to device and device to host. It cannot be reduced in this case because you only have one instance, right? So one might think that if I run multiple inference concurrently, and then we will try to use the GPU concurrent execution. With easy and direct configuration, we will run 4 TensorFlow session inference, run 4 TensorFlow inference concurrently. But look at the timeline. There's only 1 stream. Remember that on GPU, we use multi-stream to run concurrently, but actually, TensorFlow isn't taking this into consideration during its design, and it always uses a single stream for execution. But we still have performance gain. Why? You can look at the QPS, it's raised from 100 to 130. We still have performance gain. I deliberately put single instance execution together with multi-instance execution to see what happened. Since it only has one stream, the 4 threads submit GPU kernels from CPU to GPU concurrently. So look at the details of the execution. The successive kernels are from different instances. This behavior can also help to reduce part of the idle time, just as depicted in the first timeline. And in the second timeline, I give a detail of the encoder layers execution with concurrent set to 4. In the last line of this timeline, you can see that the first one in blue is the execution that belongs to a certain instance. And at the end of the timeline, it's still layer 4, and it's actually from another instance. So they are submitted into the stream 14. The stream 14 in the red box in the previous timeline, the stream 14 in a random order. So the final timeline, the whole timeline might look like this. It's still the idle time is reduced as well. You can see a performance gain in this case. So do we have methods to enable the real concurrent model execution with TensorFlow? The answer is yes. You can either use MPS by launching multiple Triton processes. There's the same critical that the multiple processes can run GPU tasks simultaneously on the same GPU and get the different kernels execution overlapped with each other. Right, and you can also use multi-stream. So in previous slide that we see, we only use one stream, and in this slide we will introduce a feature which is called the virtual GPU feature. It's experimental, and this feature allows you to split the GPU virtually for TensorFlow. So for TensorFlow, it will see 4 GPUs here in this case. I split the GPU into 4 virtual GPUs. Then the TensorFlow will create a dedicated stream for each virtual GPU it sees. In Triton, we provide this with TF-add vGPU option. Note that this is experimental and the performance gain is not guaranteed actually. Typically in this case, you should look into a better solution, says TensorRT natively supports multi-stream to enable concurrent execution. See the timeline here. The kernels from different instances are executed concurrently and overlapped with each other. This again helps a bit over previous configuration so that you can see the QPS raised from 131 to 137. But the performance is not guaranteed, so you can test this configuration in test. Apart from previous used methods, we will have more to try, such as FP16, as it can be hugely improved on Tesla T4 with Tensor Core. Combined with experimental feature used in previous slides, the QPS can reach 461.5. Another one, but very important, is batching. I will expect dynamic batching obtain a good performance gain as well as just we showed in previous ResNet 50 case, but it's not tested here. It can be a hands-on by yourself. And you can see that the QPS can, if I set the batch size to 32, the QPS is around 21.8. And if you times the 32, the batch size, it's up to around 700 and versus the 461.5, you can see a lot of improvement. And NVIDIA's another solution is BERT TensorRT. It's based on the TensorRT and optimized in a similar way. But just as we talked before, TensorRT will support the multi-stream, which is concurrent model execution here natively. And kernels and the native multi-stream support to execute concurrently will help you overlap the execution time. In many cases, only one instance is needed to saturate the GPU. So you might see a QPS is dropped from 163 to 156 if you set the concurrent to 4. But actually, it's not a performance drop, but it just gives information. With one instance, TensorRT is enough to saturate one GPU, and the performance is equivalent for different concurrency. This is a TensorRT's performance with batch size 1, and again, we will try to execute the inference in FP16. When we use FP16, the QPS of the inference is improved from 163 to 473.5, and with 4 concurrency. And you see that the average latency is very stable. It's 4.2. Remember that. Let's go back to the previous slides of FasterTransformer. You can see the FasterTransformer's concurrent execution average latency is around 9 milliseconds if you get a QPS around 460. Actually, the TensorRT's inference is a little bit stable than the FasterTransformer deployment because TensorFlow also introduces something unknown into the deployment. Next is batching. Batch also helps with the TensorRT inference. The QPS of TensorRT in FP16 precision is around 30.5, and time if 32, that you might reach 976, and it's compared to the FasterTransformer's highest QPS. And compared with the 473.5 QPS, this is the case when the batch size equals 1. The final attempt is trying to scale out the deployment to use. Here we have 2 Tesla T4. The QPS is scaled linearly across 2 GPUs, and the latency is good. Actually, Triton is very good at load balancing within a single node. It usually has 4 to 8 GPUs. Triton also has a lot of integration solutions with Kubernetes and Kubeflow for you to scale out to tens of thousands of GPUs. And this is becoming quite common in nowadays online inference systems. With this case study, I think we covered a lot of optimization skills of BERT inference, and we also discussed about how to improve your deployment with Triton Inference Server's powerful features. So beyond this, I think there are a lot of new algorithms and techniques such as AR BERT, which is light BERT and tiny BERT, and a lot of other BERT variants. Techniques adopted here might be pruning, weight factorization, knowledge distilling, weight sharing, quantization, pre-train, pay attention to the downstream tasks. They have single or multiple improvements, such as a hardware accelerated low precision computing. And we will also do some experiments on int4 inference on Tesla T4. And usually we will have less memory footprints. Then this will help to enable larger model training or faster inference. And with different algorithms, we can have better model scores, and less complex architecture will always give you a fast inference or smaller models. So you can try to experiment with your models and try to deploy that with Triton Inference Server on Tesla T4. And I've talked about the key features of how to improve the deployment on the GPU, and just try them out. We also provided a lot of materials for you to learn more and download to use the Triton Inference Server. We have dev blogs, and we also have the ready-to-deploy container from ngc.nvidia.com, which is the container registry we provided. And we also provided a lot of other container images and for you to reproduce the results to try our optimized inference, optimized framework such as TensorFlow, PyTorch, MXNet with multi-node training scripts support natively, and a lot of other things. Here is a list for additional resources, and you can have refer to these materials to have more information about Triton Inference Server and also our latest updates. We've already put everything on the GitHub, and we also have well-documented documentation. So just to refer to them. Okay, I think today I've talked about how to deploy the models with Triton Inference Server in an efficient way, and I've also NVIDIA's BERT inference optimization skills and the solutions. So you can have a try with the scripts or with steps from my GitHub to get a similar result. So you can hope that can help with the deployment in your actual production environment. So thanks, and we can have a Q&A. Let me go through the questions in the Q&A. Okay, one question is about does NVIDIA optimize the decoder of transformer, and can I serve that with Triton Inference Server? This is a good question, and actually we released the decoding implementation of transformer in FasterTransformer, and just a couple of weeks ago, and you can certainly serve that with the Triton Inference Server and try to get a good performance. I think in some cases, because you want to using decoders, that might be related to the streaming API. Maybe you can try that feature as well. Another question is about how much does the accuracy drop when you switch to FP16 for BERT? Yes, it's a very good question. Actually, it's almost no accuracy drop if you use FP16 for BERT inference. And we've done a lot of tests to make it happen. And we also pay a lot of attention to the int8 inference. Actually, we've already doing experiments with this, and possibly if we have some results, we might release them as well. And as far as I know, a lot of our customers have already applied int8 in some layers of BERT, and it reaches a good, very good result. One question is is a virtual GPU feature similar to the simultaneous multithreading CPUs called hyper-threading by Intel? Actually, I think the virtual GPU introduced in TensorFlow is just how give a view to TensorFlow and let TensorFlow see there are 4 GPUs. And actually, I think TensorFlow introduces this feature to handle something like the model concurrent execution, and I don't think that's much related to the performance. So I think it's not similar to the simultaneous multithreading, but some tactics for TensorFlow to handle the GPU memory to help you control the memory of each of the session. One question here. What is a plugin for TensorRT? Sorry for not introducing the plugin for TensorRT. Actually, a plugin for TensorRT is some features that let you extend the TensorRT's ability. For TensorRT, there are a lot of native layers that can be supported by TensorRT, but nowadays there are a lot of new layers and new OPs introduced by researchers. So if you want to import models into TensorRT or build models in TensorRT with very new OPs that's not recognized by TensorRT, you can handwritten some code for TensorRT and just tell TensorRT how to execute that code. So in this case, you can write something named plugin for the TensorRT so that TensorRT can execute your model. One question here is about when do we need dynamic batching and when do we need concurrent model execution? Actually, it's a very good question because, in a real production system, it might be very complex. And in my slides, it's the first time the timeline assumption is very simple and it cannot reflect in the real production system. So actually, you can try to use dynamic batching or the concurrent model execution just to see whether which one is better. And for some cases, the dynamic batching might work, but for the TensorFlow execution, you might need multi-stream, but TensorFlow natively doesn't support the concurrent model execution. So in these cases, you might have different choices for you to try out. One question is about for enabling dynamic batching, do we need to change any model architecture, or can we do it by just specifying the configure file? Actually, if a model supports batching, you can just specify in the configure file. And if the model doesn't support batching, you have to modify the model architecture so that the Triton Inference server can apply dynamic batching to that model. Here's another question. If I have an in-house framework, how should I deploy models with Triton Inference server? Actually, I introduced the custom backend. You can extend the Triton Inference server's ability with custom backend to do some image processing or image post-processing. And you see that this is something like a specific task. I think you can extend your in-house framework using custom backend. But another option is to extend the base backend just similar to how TensorFlow or TensorRT is supported in Triton Inference server, so that you can use the 4 features or the 4 functionalities that's defined in Triton Inference server. one question here is about how about Int16? Is that good enough for BERT inference without obvious accuracy drop? Or FP16 is a minimum precision in engineering right now? Actually, I don't have experience with Int16, but for FP16, there are two reasons why we would like to use FP16. The first one that we can reduce the memory footprints and reduce the requirement of memory bandwidth when we do the inference in FP16. And another one is that on Tesla T4 or some other GPUs, we support Tensor Core's FP16 multiplication so that it can be greatly improved in view of the performance. That's why we use FP16 here. Actually, we have for FP16 we have different standards, such as the IEEE FP16 and or something like a B float. And I think FP16 is also different in the training case and the inference case. And we just use IEEE FP16 here on Tesla T4. One last question here is does the vGPU feature only work with higher-end hardware? I don't think so. I think vGPU feature actually it's introduced by TensorFlow, and here we just use it as an experimental feature to see whether we can make the concurrent model execution benefit our deployment. And I think it's depending on how you use it. And even if on a low-end hardware, you can still split the GPU into several virtual GPU to see if you can have performance gain. And if not, maybe you can try some other features that introduced in previous slides. So I think we've almost run out of the time, and thank you for listening to my sharing. And I think if you have more questions, you can we can discuss offline, and you can also send emails to me. And on my GitHub, you can refer to my steps to reproduce results I introduced today. So thank you.